Now, what about the energy of rotation? Just like a cute little panda here. And that energy is made up of linear component and a rotational component because as we're moving across the surface, we are both translating and rotating without slipping. So we're not using kinetic friction, we're using static friction if we were asked, but they typically don't ask that in these problems. So what does that look like? The linear kinetic energy is 1/2 mv squared plus the rotational energy of 1/2 I omega squared. So since I is different for each different shape is going to have a different rolling kinetic energies. But we're going to use a disk because wheels are typical things that we see rolling down the hill. The I for the disk is 1/2 mr squared. So we're going to substitute that in for I here. So we get 1/2 mv squared plus 1/2 now 1/2 mr squared. And I'm also going to substitute in this definition of omega is v over r, so we get v squared over r squared. And like we saw previously, these two r's will cancel out. So then I have 1/2 mv squared plus 1/2 times 1/2 is 1/4 mv squared. And now I have 1/4 mv squared and 1/2 mv squared. So that gives me 3/4 mv squared is my kinetic energy for a disk rolling. This is only for a disk because every different shape will have its own I. So I rolling for a disk is equal to 3/4 mv squared. So here are those values again. And then how is that useful? Well, when we're looking at an energy balance, we want to know what the final speed is when we come down a ramp. And that final speed we can predict using an energy balance. So this is the same energy balance that we've done several times before, where we're looking at the trade-off between potential energy and kinetic energy. So at the top of the slope here, I started out with potential energy initial, and these problems don't typically have any work done on them because we're not slipping against the surface and we're not being held by the surface. And that is equal to our kinetic energy final. And so potential energy is equal to mgh at whatever height I start at up here is equal to kinetic energy final. And we just said that for a disk, that is 3/4 mv squared. And the m's cancel out just like we've done before. And so v for a disk rolling down the hill is the square root of 4/3 gh. So we can easily predict how fast it's going to go down the hill. Then the question is, let's have a race. So we have a hoop and a solid disk. They both have the same mass and And so what would happen if we send them down at the same time? Who's going to win the race? So for the disk, we got the velocity of the disk was 4/3, the square root of 4gh. So what would that look like then for the hoop? So the first thing we need to do is figure out what the kinetic energy of rolling for the hoop is to be able to do that very same energy balance. So for this guy, we said I is equal to 1/2 mr squared. For the hoop is just I is equal to mr squared. That means we have 1/2 mv squared plus 1/2 I omega squared, where again we're going to do the same substitution for I, but this time using the I for hoop instead of a solid disk. So we get 1/2 times just mr squared here. And then omega squared is equal to v squared over r squared. Again, those r's do cancel. And so we get for the hoop that the rotational kinetic energy is 1/2 mv squared plus 1/2 mv squared. And 1/2 mv plus 1/2 mv is equal to mv squared. Then I can do the energy balance. So energy initial plus work is equal to energy final. Again, that goes to 0. So we get mgh is equal to, now it's just mv squared. It feels kind of weird to write it without the 1/2, but that means the velocity for my hoop is equal to the square root of gh. So what does that mean? Is that the velocity of the disk is 4/3 gh, and we want to compare that to gh. This number is bigger than 1, so this number is bigger, and that means the velocity of the solid disk will always be more than the hoop, and that means it will win the race because it is moving, it's translating. This v means the translational speed is translating faster than its hoop, and we can see that in these videos. So here is a video of a disc and a hoop racing, and clearly the disc wins, and that's because it's putting less of its energy budget into rotating. It's able to put more of its energy bucket into translating because it does not have to spend as much energy to simply in rotation. And what happens if we add more shapes? So here are a variety of shapes, and they finish in order of the moment of inertia. The hoop always loses because it's always got the highest moment of inertia.